Welcome everyone to this section on generative adversarial networks. Generative adversarial networks, or GANs for short, were invented in 2014 by Ian Goodfellow and his fellow researchers. And the main idea behind them is to use two networks competing against each other to generate new unseen data. GANs are often described as a counterfeiter versus a detective. Let's get an intuition of how they work. So, we can think of the counterfeiter as the generator. The generator is going to receive random noise, typically a Gaussian or normal distribution of noise, and then it's going to attempt to output data. So generators are often used for image data. The discriminator is the detective. It takes a dataset consisting of real images from a real dataset and fake images from the generator, these counterfeit images, and it attempts to classify real versus fake images. So keep in mind, regardless of your source of images, whether it's something like the MNIST dataset that had 10 separate classes, the discriminator itself is always performing a binary classification. It's just trying to tell if something's real or fake. So let's actually see this process. We first start off with just some noise, some Gaussian distribution of noise data, and we feed that directly to the generator as input. The generator goal is to create images that fool the discriminator. So keep in mind, in the very first stage of training, what's going to happen is the generator, given noise, is just going to produce noise. And then we also grab images from our real data set. And then what we do is in phase one, we train the discriminator, essentially labeling the fake generated images as zeros, and then the real data generated images as ones. So basically 0 if you're fake, 1 if you're true. We feed that to the discriminator, and the discriminator then gets trained to detect a real image versus a fake image. And then, as time goes on, the generator, during the second phase of training, is going to keep improving its images, trying to fool the discriminator, until it's able to, hopefully, generate images that appear to mimic the real data set, and the discriminator can eventually no longer tell the difference between the false generated image versus a real image. So there's really two training phases. Phase one is training the discriminator, and then phase two is training the generator. In phase one, what we do is we take real images and we label those as 1 for being truly real, and they're combined with fake images from a generator, labeled 0. The discriminator then trains to distinguish real images from fake images. Keep in mind, in phase one of training, the backpropagation is only occurring on the discriminator. So we're only optimizing the discriminator weights during phase one of training. Then in phase two, what we do is we have the generator produce more fake images. And then in phase two, we only feed the fake images to the generator with all the labels set as real. And this causes the generator to attempt to produce images that the discriminator believes to be real. And what's important to note here in phase two, because we're feeding in just all fake images labeled with 1, we only perform backpropagation on the generator weights in this step. So we're not going to be able to do a typical fit call on all the training data as we did before. Since we're dealing with two different models, a discriminator model and a generator model, we'll also have two different phases of training. What's really interesting though, and something you should always keep in mind, is the generator itself never actually gets to see the real images. It generates convincing images only based off gradients flowing back through the discriminator during its phase of training. You should also keep in mind the discriminator is also improving as training phases continue. So, meaning the generated images will also need to hopefully get better and better in order to fool the discriminator. This can lead to really impressive results. NVIDIA Research has published many models, such as StyleGAN and also a FaceGAN, to actually produce fake human face images that are extremely detailed in nature. So all of these faces you see here were actually generated using a GAN-based system. So pretty impressive results. Now let's briefly talk about the difficulties with GAN networks. And those are things like training resources, mode collapse, and instability. And we'll also try to give you potential solutions for each of these problems. So right off the bat, GANs are most often used with image-based data. And Due to the fact that you have two networks competing against each other, they usually require graphical processing units or GPUs for a reasonable training time. Now, fortunately for us, Google Colab currently has GPUs available for free, as discussed in the setup lecture. But just keep in mind, realistically, when you're training GANs, you're not really going to be able to train them on CPU. It'll just take too long. The next problem that occurs with GANs is something called mode collapse. So often what happens is the generator will figure out just a few images or even sometimes a single image that can fool the discriminator. And eventually it collapses to only produce that image. So you can imagine that back in that situation where it's producing faces, maybe it figured out how to produce one single face that fools the discriminator. Well, then the generator ends up just learning to produce that same face over and over again. So in theory, it would be preferable to have a variety of images, such as multiple numbers or multiple faces or multiple images, etc. But GANs, again, can quickly collapse to only produce a single number or a single face or a single image, whatever your data set happens to be, regardless of the input noise, which means you can feed in any type of random noise you want, but the generator figured out the one image that it can use to fool a discriminator. So in its batch of images that it just produces copies of the same image. Now, a couple different ways of trying to fight this problem is by using deep convolutional GANs, which we'll see later on in this section of the course. And they're typically better for avoiding mode collapse because they are more complex and they have deeper layers to them. Now, researchers have also experimented with what's known as mini-batch discrimination, which essentially punishes the generated batches of images that are all too similar. So if the generator starts having mode collapse and getting batches of very, very similar looking images, it will begin to basically punish that particular batch inside of the discriminator for having the images be all too similar. And the last problem that we discussed was instability. And it can be difficult to ascertain performance and appropriate training epochs since all the generated images, at the end of the day, they're all truly fake. So it's difficult to tell just how well your model is performing at generating images, because just because the discriminator thinks something is real doesn't mean that a human like us will think a face or a number looks real enough. So it's always difficult to ascertain that sort of true performance. And again, due to the design of the generative adversarial network, the generator and discriminator are constantly at odds. They're fighting each other. So that can lead to performance oscillation between the two. So typically, when you're dealing with GANs, you'll have to experiment with hyperparameters such as the number of layers, number of neurons, activation functions, learning rates, etc., especially when it comes to complex images. A few final thoughts before we continue on to actually creating our own GANs with Python and Keras and TensorFlow is that GANs are a very popular area of research, and often the results are so fascinating and so cool that researchers even like just to do this for fun. So you'll see a ton of GitHub repos on all sorts of different GANs. So I would highly encourage you to make sure to do a quick search on Google Scholar for the latest research papers on this topic. This is something that you'll see a paper almost every month just on some really interesting research in generative adversarial networks. So I highly encourage you to just do a Google search and see what has come out in the last few months. Okay, with that being said, let's get started in programming our own GANs. I'll see you at the next lecture.